This is Common Core State Standard Support video for mathematics. The standard is 5NFB4B. This standard reads, apply and extend previous understandings of multiplication to multiply a fraction or whole number by a fraction. The particular standard that we're addressing today is Part B. Find the area of a rectangle with fractional side lengths by tiling it with unit squares of the appropriate unit fraction side lengths, and show that the area is the same as would be found by multiplying the side lengths. Multiply fractional side lengths to find areas of rectangles and represent fraction products as rectangular areas. Well, first let's look at some of the other standards that this is connected to. If you look at standard 5NFB6, it has a connection to this one. Solve real-world problems involving multiplication of fractions and mixed numbers by using visual fraction models or equations to represent the problem. So that's what we're doing with 5NFB4B. We are going to be using models to represent what's happening. Standard 5NFB4B is also related to standard 5NFA1, which states add and subtract fractions with unlike denominators, including mixed numbers, by replacing given fractions with equivalent fractions in such a way as to produce an equivalent sum or difference of fractions with like denominators. So we will be doing that today because we will have to be combining fractions that do have unlike denominators. Let's address the first part of the standard. Find the area of a rectangle with fractional side lengths by tiling it with unit squares of the appropriate unit fraction side lengths. So let's take something fairly simple. Let's go with 3.5 by 2.5. Now it's a good idea to actually have a model that's larger than 3.5 times 2.5. Let's round it up to the next whole numbers. So let's make it 4 by 3 so that students can see exactly where the fractions come from. So just by looking at this visually, students can determine what the fractions actually are, as well, of course, as the unit squares. So all students have to do now is just count them up. Okay, so here we have 6. So we have that so far. And we have a couple of halves here, so that's a 1. We have a couple more halves here that'll make another 1. So let's combine all our whole numbers so far. That's 8. Now we have the 1/2, so that just makes it 8.5. And all we have left now is the 1/4, which we combine with the 8.5, and so we get 8 3/4. So what we really have here is 8 unit squares, 8 1 by 1 squares, and 3/4 of another 1 by 1 square. Let's address the next piece of the standard. Show that the area is the same as would be found by multiplying the side lengths. Okay, let's take 3.5 times 2.5, but let's expand it out. Let's use our distributive property so that we can see exactly what originates from what based on the partial products. First we multiply 3 times 2, and if you connect it back to the model, here's 3 sets of 2, which will give us 6. So that takes care of that so far. Next we have to multiply 3 times 1/2, and if we connect that back to our model, oh, there's 3 halves right there, which would be 1.5. Now we have to multiply 1/2 times 2. But it might be better to look at this as 2 halves. That way when we look at our model, oh, here's the 2 1/2. So that gives us 1. Last but not least, we have to multiply 1/2 times 1/2. And if we connect that to our model, there's our 1/4. And all we have to do now is combine everything. Let's take our whole numbers like we did a while ago with just the tiling. So that gives us 8. Then we have this 1/2. And all we have left is the 1/4, which we combine with the 8.5 to get 8 3/4 like we did earlier. And again, that's actually 8 unit squares plus 3/4 of another one. Now let's use that same model to address the last piece of the standard. multiply fractional side lengths to find areas of rectangles, and represent fraction products as rectangular areas. Okay, so we'll start off with 3.5 times 2.5. If we use our standard algorithm, we convert those to improper fractions. Then we multiply our numerators, multiply our denominators. We get 35 over 4. But what does this 35 over 4 really mean? We need to make sense of it and connect it back to our model. Let's look at 7 over 2. What's really happening here is that you have 7 halves. So each one of these lengths, like here, that's a distance of 1/2, and we have 7 of those. Likewise, when we look at the other dimension, our 5 halves, that's 5 lengths of 1/2 each. So we multiply 7 times 5 and we get 35, but exactly what is that 35? What does it really mean? And the same thing when we multiply 2 times 2 to get 4. Well, let's start with the 4. Let's start with the denominator. If we look at our unit square at the bottom, it's 1 by 1, be it 1 centimeter by 1 centimeter or 1 foot by 1 foot, whatever the dimensions are. And notice that we have 1/4 of it shaded, so we have an area of 1/4. Okay, now it starts to make a little bit more sense. Each one of those really small squares is 1/4 of a 1 by 1 square. And so if you count these up, we do have 35 1/4. So what the 35 really means, we have 35 area units, and each of those is 1/4 the area of our unit square, which would be, of course, 1 by 1. So in this context, multiplication is a process by which the linear units get converted to area units. Let's take a closer look. Again, let's say we have 1/2 times 1/2. So here's 1/2 by 1/2, and when we multiply it together, we get 1/4. And that's 1/4 of our unit square. So shouldn't we call it square units instead of just area units? Well, let's take another example. 1/3 times 1/4. So take our unit square, divide it up into 4 equal lengths one way, and then by 3 equal lengths the other dimension. So each one of these is 1/3 by 1/4, which is 1/12 when we multiply it. And so what we really have here is 1/12 of a 1 by 1 unit square. Now notice, wait a minute, 1/3 by 1/4, that's the dimensions of that smaller rectangle, and that's not a square. So we have to be careful. I think it's better to use the phrase area unit as opposed to square unit, because students might get confused because, again, these units here are not each squares. And that's going to happen. We used the first example. It did turn out to be perfect little squares because they were all 1/2 by 1/2, but that's not always going to happen. You're going to have situations like this where you might have something like 1/3 by 1/4. So let's look at another example. 2 3/5 times 1 2/3. Again, let's start with a larger model. Let's start and make it 3 by 2. So looking at this dimension, we have 1, 2, and then our 3/5. And then looking at the other dimension, we have 1 and 2/3. So vertically, we split this up into thirds. This way, we split it up into fifths. And of course, remember that we're only dealing with this area in here. That's going to be our product. We eliminate all of this out here, but we need this diagram so students can, again, understand where all these fractions come from. So let's walk through our model and see what actually happens. If we take our 2 3/5 times 1 2/3, and let's use our distributive property. and change it to 2 plus 3/5 times 1 plus 2/3. We start off, we multiply 2 times 1. And so here's 2 1s, so we have 2 unit squares. So we have that so far. Then we have to multiply 2 times 2/3. Now, these dimensions here are 1/3. And if we look at the model and try to connect it back to what's happening with the multiplication, here's 2/3 here and here's 2/3 there. So there's our 2/3. And let's go ahead and shade them in a different color so students can tell what's what. Now we continue on. We have to multiply 3/5 times 1. And we connect that to our model. Here's 3 1/5 right here. So we have 3/5 of our 1 by 1 unit square. Shade those in again in a different color. Then the last partial product, 3/5 times 2/3. If we look at the bottom right, here's our 1 by 1 unit square. And it's split up in 5 equal pieces one way and 3 equal pieces the other for a total of 15. So each one of these smaller rectangles is 1/15 of our unit square. There's going to be 15 of those. And so we have 6/15 for our product here for the last multiplication. So now if we go ahead and multiply it out, although we've already kind of informally done that with our physical model, 2 times 1, okay, there's our 2. And then 2 times 2/3 in simplified form and as a mixed number would be 1 1/3. 3/5 times 1. And then 3/5 times 2/3 is 6/15. We combine those whole numbers to be a 3. So we've taken care of that, and it connected back to our model. Now let's go ahead and work it using this method. We get a common denominator so that we can combine these, and so that we have 15ths. 5/15 plus 9/15. Okay, now our 6/15, that's our last partial product. That's represented physically down here. And the 1/3 here, we had converted to 5/15. So we convert our model to match what we have with 15ths. And then this is our 3/5 times 1, which again was still 3/5. We converted that to 9/15. So there they are. So when we combine all the 15ths, we have 20 of them. Convert our 20/15 to a mixed number, so it's 1 5/15. Now let's connect this to the physical representation. This one here, what we can do is we can take, for example, these 3/15 and move them here, and these 3/15 and move them here. And that is a whole 1, so we can combine the 3 and the 1, we have 4. And all that's left is our 5/15 there, which of course simplifies to the original 1/3. So our final solution will be 4 1/3 in simplest form. Let's retrace our steps and maybe take a slightly different approach this time. Let's take our 6/15, and this time let's simplify that to 2/5. Now we can combine 3/5 and 2/5. That's a nice easy addition because that's just going to be a whole of 1. A way to connect this slightly differently to our physical model, we can take this 1/15 and move it over here. and take this 15th and move that down there. And look what we have. So this 3/15 is 1/5. This 3/15 is 1/5. And when we slide them up in here, that gives us a whole of 1, which corresponds to this one here. We can now connect all of our whole numbers. We have 1, 2 here, so that takes care of that. We have these 3 1/3 here, which takes care of another whole number, another 1. And then we already saw that these 15ths and these 5ths can be combined to be another whole. So there's a whole of 4. So everything is accounted for except for the 1/3, which of course is right there. And so now we made a connection from our abstract, from our multiplication over here to the actual physical model here. So our final solution is 4 1/3, and again, we've made connections so that students can see exactly what is represented where and where all these different pieces and all these different fractions come from. Let's take a slightly different approach, and again focusing on this last part of the standard that deals with multiplying fractional side lengths to find areas of rectangles and represent those fractional products as fractional areas. This time we're going to use our standard algorithm, change the 2 3/5 and the 1 2/3 to improper fractions, do our multiplication, and we get 65 over 15. We've already had a little bit of experience with this, so we have a better notion of what represents what. So the 65 is actually 65 of these 1/15ths. We have 65 15ths. Each one of those 1/15ths is actually an area amount, and again there's 65 of those in the total diagram. And again, keep in mind that the dimension of each one of these is 1/3 by 1/5. Again, the temptation is going to be to say 65 square units, and each of those is 1/15 of a unit square. But again, they're not really little squares, they're actually just little rectangles. So again, we have to exercise caution when we use that phrase, square units. Might be a little bit more accurate to say 65 area units. And again, each one of those is 1/15 of a unit square. When we simplify 65 over 15, we get 4 1/3, which is the exact same product that we got earlier when we used the distributive property. But let's connect this to this diagram and see where the different pieces come from. If we were to take this section here, these 5/15ths, and move them over here, we'll make a unit square. And if we take these 15ths here and move them here and here, there's 6 of them that we could fit in these 6 open spaces, and so we'll have a unit square here. And so now here's what we've created. We have our 1, 2, 3, 4 unit squares, and then we have 1/3 of another unit square. So we have a total of 4 1/3 square units. And to be absolutely sure again that students understand what this really says, we have 4 unit squares and 1/3 of another unit square. And again, use caution with the phrase square units. Connecting this to the standards for mathematical practice, our first 4 are listed here. Looking back at the activities that we did, we can safely say that we have applied numbers 2, 3, and 4. We reasoned abstractly and quantitatively. We constructed viable arguments and critiqued the reasoning of others, especially if you have students do this in groups, group assignments. We did model the mathematics. If we look at the other 4 standards for mathematical practice, 5, 6, 7, and 8, through our activities we addressed number 6 and number 7. We did attend to precision, and we looked for and made use of structure.